Okay, great. So I will start today. First of all, welcome friends to AI Club. I am Shailendra Kadre. A couple of classes we have already done on ANN. So one of them was a very comprehensive theory class. And in yesterday's class, which is Saturday, same time we took a class. So that time we did uh, regression, simple regression with the help of ANN models. And we did a couple of ANN model and we compared them how they compare to each other. So we learned basically ANN based regression. That is what we have learned. So yesterday I think we have left we have something which I promised you to explain today, which we couldn't finish yesterday. I was a bit confused in yesterday's class. So that was screen visible, right? So this cross validation score, right? So this cross validation score, here we are passing estimator. So estimator we are taking from Keras regressor. So in classical machine learning, we import linear regression, right? So in TensorFlow, we import the Keras regression in that place. So Keras regression does the same job. It is a wrapper method. So in that case, we pass the model, we pass the epoch, and batch size we give, and verbose 0. All these things we did yesterday. Now, when we do cross validation score, we take an instance of this Keras regressor, which is estimator. We have given the name estimator. So that estimator name we give, we pass X train, Y train, and K-fold. So K-fold means we are doing, for every epoch, we are doing 5 times. K-fold we have given 5 times. In K-fold, we have given n split is 5 means for every epoch, it will run 5 models. Okay. So what it does, it does internally training happens and evaluation also happens. And here we have not given any scoring. So default scoring, it picks up default scoring. And based on that scoring, both training and testing happen. And when we print, so best error is whatever default parameter it took to do the model evaluation. It took some default parameter. So that value is minus 29.76. And its standard deviation of 5 values. 5 results will come, right? Because 5 models have been done. So standard deviation of 5 values was 3.5.337. That's what it is. So, but now what I need to do some kind of some predictions also, because doing prediction on any regression model is what the productive job I want a model to do, right? I want to always do predictions on the model. But on Keras regressor, whatever we have taken a instance, in Keras regressor, we don't have that predict method. So even if in this cross evaluation score, all training or testing has been happened, but since this Keras regressor doesn't have predict method, we have to do once again training and do training and predictions. So, in spite using cross validation score once, on the same estimator, we are calling fit method once. So on the whole training data, we are doing the training. So here cross validation score is doing what? If you remember cross validation score, it divides the whole training data set into, say, we have given n split equal to 5, so it has divide that into 5 parts. Data set it will divide into 5 parts. Okay, so a small portion of 1/5 portion of the data set, it will do the training cross validation score. But here, since this Keras estimator doesn't have predict method, we have to do training once again. So now this we are using estimator.fit. We are doing training once again on complete train set. We are doing training complete train set. So once we do this kind of training, then we have we get a estimator which has proper prediction and all that. Okay, so means even if you apply cross validation score, once again you have to do the training. That's what you have to remember, because we want to use predict method. That predict method is not available in Keras regressor. That's why we do one training once again. Once we do training, in this estimator, we have predict method also. We have predict method also available. And with this predict method, we are using this analyze function. And if you see this analyze function, we are using this analyze function. First of all, we are doing analyze function. See here model. Yep, we are passing model as a parameter. Model as a parameter. Here we are passing train X and train Y. So model dot predict we are using. We are doing predictions. With the predictions, we are calculating residuals, and then we are calculating usual R square and doing our plots. Okay. So even if you are using cross validation score, the estimator which will come out of this will not have predict method. So we have to do training once again. So that's what we have done here using fit. And once we do this fit, then you have proper predict method available. So then which you can pass through analyze and get all your root mean square error, R square, and you can plot all this kind of graph. So that's why we are doing training twice. And one difference here is that here at a time training is happening on only 1/5 of the data set, because n split we have given n split equal to 5. So whole data set has been divided into 5 parts. So cross validation score will do training at a time only on 1/5 of the data set. Here when we do estimator.fit, complete train and test we are using. Okay. So that's how we get predict method, and with the predict method, then you can do your usual stuff. So that's, and today's session, I think we'll keep a bit short, because most of it we covered in yesterday's session only. And today, after this, we are, all this we discussed was Keras regression, means ANN regression we were discussing. So now we'll get into something called Keras classification. So Keras classification, you will find that the code is very similar to Keras regressor. So same, we are taking a sonar data set. So we read the data set. We read the data set and we display the data set. You see there are some cryptic columns A1, A2, A3, A4. So they are all, I think, some kind of processing has been done on this, some kind of standardization or processing or principal component analysis is applied. They want to hide the actual data. They don't want to share actual data with you. That's why they have done some kind of principal component analysis or some kind of standardization they have done, and they are giving this kind of coded data to A1, A2, A3, A4, so that you don't make out what kind of fields they have. So like that they have, so we are not concerned also. We have 60 dependent variables. We have 60 dependent variables, and there is a target variable with the name target. So we have to predict whether it is yes or no. Okay. So then we do usual data info and all that. So you see null. So there all the 60 column, all are fully populated. There are no null values. Same results here also. We have seen this. We had seen this yesterday. Then we separate X and Y. Usually what we did yesterday also, we separated X dependent variable and independent variable. Both we separated. So we have now X and Y. After that, we have done same train and test split, which we did yesterday. Same code here. Then we see the shape, counts. So like counts means in this data set, M category is having 89 records and R category is having 67 records. So one of them you assume as yes, and one of them you assume as no. So there are only two categories, M and R. So one you can assume as yes and one you can assume as no, 0 or 1, like that. So it is a very balanced data set, 89 and 67. So around 60-40 or something like that. M is to R ratio is around 60-40. It's a very balanced data set. So now then again you have to do imports. So you import accuracy score, average precision score, then confusion matrix, ROC curve, precision recall curve. ROC curve you are again importing log loss. So why you are importing log loss? We'll see it in the code ahead. We'll see. Then recall score and a lot of other metrics like F1 score, beta score. All these metrics he has imported. Okay. And he has one importantly, he has imported is log loss also he has imported. Now he is making same analyze he is making analyze tool. So in the analyze tool, what he has done is that he has done confusion matrix. So confusion matrix has been confusion matrix. You see all the true positive, false negative. So this everything we have covered in logistic regression. Then he has calculated. Once you have confusion matrix, means you can calculate accuracy, precision, sensitivity, specificity with simple formulas. He has calculated F1 score also, and he has calculated some new matrix called F beta score. So I think even I want to do some research on what is this F beta score, because it is very rarely used. Generally F1 score and ROC AUC what we use. So this F beta score we have to see what it does. So maybe you can do your own research on what this new matrix F beta score stands for.
Sir, F beta score is same as F1 score, but in case you need to give importance to either recall or precision, you can do that by adjusting the beta value.
Okay, but we need in little more detail, na? So yeah. I think we better do some R&D on our own, because simply if you explain something, it gives us some idea, but it doesn't explain it fully, right? So
the generic this one here he has set to beta equal to 2. So this is F2 score actually.
No, madam. It is F1
no,
score only.
It is the same F1 score. The F1 score, the definition is same, the harmonic mean of recall and precision. But in case you have to give more importance to either recall or precision, because we are calculating both scores, na, recall and precision together. In case we have to prioritize either of them, so that's why we adjust beta. So beta actually refers to how much importance compared to precision you are gonna give to recall. So beta equals to 2 means double the importance to recall as compared to precision.
Yeah. Thanks someone for adding that. But I would like all the learners here to do some kind of their own research and find it out what is this F beta score. Even I will do after this call. And then you have made data frame, and then it is nothing but some graphs they are plotting, and ROC-AUC curve is plotting, and PR-AUC curve is plotting. So that I think this I will need not go into detail, because these are all very well covered in logistic regression. So you can, once you see the core, you will understand. And in fact, you can use same function. It is a beautiful function. You pass the model, whether it is a regression model with logistic regression model, or random forest classification, or XGBoost classification, or ANN classification, any model you pass, then you pass either train or test, both train or test you can pass, and then title you can pass. So it will all the plots it will do automatically for you. So for your rest of your professional career, you can use the same code. I think just copy this code, pass these two things, and it will give you nice plots, as we shall see ahead. See, again, same model, we are importing sequential model from Keras, then dense layer class we are importing. And now instead of Keras regressor, we are importing Keras classifier. Same class validation score. And now instead of one-hot encoding, he has used level encoding. But as I told you sometime back, I think, label encoding, using label encoding to encode your categorical data, how much wise it is questionable. Because in label encoding, 1, 2, 3, 4 kind of encoding will be done in the same column. If there are 5 classes, so it will be encoded as class 1 will be encoded 1, class 2 encoded as 2, like 3, 4, 5. So like that we have and 1, 2, 3, 4, 5 represent some kind of weights. So if you use label encoder, then unnecessarily class which is encoded at 4 and 5, 3, 4, 5, you are getting them more weightage than 1 and 2. So how much wise it is? I think we have to do some research. Like this model has used label encoder. I will suggest you to use one-hot encoder. It will do the same job. And then compare the accuracy and all the model parameters with the level encoder, which is better. Okay. So I just kind of made you, I have sensitized you that label encoder may not give that great results, and instead one-hot encoding may give better results. So, but it has come from a very good source. So I believe there might be some reason he has used label encoder. But I will suggest when you practice at home, instead of label encoder, you simply use one-hot encoder and compare the result with this model. Then it will tell you which encoder is better. So encoder he has used. On encoder he has fit white train he has fitted. So white train, why he has fitted white train? Because white train only is you see categorical. So white train, some 89 values are N and 67 values are R. So it is only categorical column. Rest all you see here, all are numerical columns. All 60 dependent variables are already numerical columns. And there is no null value in that. So there is no treatment required. And already scaling has been done. Already you can see they are calibrated. Already scaling has been done. So you need not apply any standard scaler or anything to this data. Already it has been done. Okay. So it has used standard scaler, label encoder. To the label encoder, there is only one column you have to fit white train and white test. So fitting you will always do on white train, and you will then transform white train, and then on white test you will not do any fit. You will do only transform. I think this thing we have already discussed many times, that on white test, why don't we use fit? Dot fit we never use on white test. Dot fit we always use on white train, and white test we use only transform. So these things I think already we have discussed in previous classes. And if you are not familiar still, I would like you to do some web research that in encoder or any kind of scales while using encoder or using standard scaler or min-max scaler, we do fit only on train data. We never do fit on trace data. So what is the reason? I think I would like you to do some kind of research. And I think these multiple times we have discussed in our classes. So I will not repeat. So let us create a model. A simple model has been created, baseline model. Model equals to sequential. Yesterday we have discussed. Added first dense layer. Input neuron, new number of neurons 60. Input dimension also 60. There is no controversy. Activation in the first layer is ReLU. Then second layer is your classification layer. Okay, it is a classification model, right? It is a classification model. But since there are only two classes, M and R, which is yes or no, we need only one neuron. Because classes are only two. So if it is more than 0.5, we will classify it as 1. And if it is probability is less than 0.5, we will classify as 0. So only one neuron will do. But here there is one important thing. In Keras regressor yesterday, while regression problem we didn't add any activation. We can add linear activation, that is optional. But we didn't do anything. Just like that value were coming, we represented without any transformation. Whatever number was coming to the last neuron, output neuron, we represented it just like that without any transformation. But here you cannot do that. Here it is a two-class problem. So two-class problem means you have to add a sigmoid function. And why we are adding a sigmoid function? Because whatever a value comes on the dense neuron on the last layer, output neuron, whatever value comes, it will be a continuous number. It will be a number, some number kind of. It may not be between 0 and 1. It may be some number. And we want probabilities. Our answer, it is a classification problem, right? We want probabilities, and probabilities always lie between 0 and 1. Probabilities always lie between 0 and 1. So we want our answer between 0 and 1. If probability is above 0.5, we'll classify as 1, and below 0.5, we'll classify as 0. Right? We want probability between 0 and 1. So whatever number comes, whatever transfer number comes to this neuron, we need to transform it between 0 and 1. So we have to apply a transformation. So this sigmoid transformation we are applied. And this sigmoid transformation we had studied sigmoid function. We had discussed it in very detail at the time of studying logistic regression. If you have forgotten, I will suggest you to go back to logistic regression video. It is available on our channel. Just have listen to or look at my PPTs. You will find the discussion about sigmoid function. So sigmoid function, what it does? whatever number comes to this last dense layer neuron, it converts it into between 0 and 1. So that's what we want, right? So here activation function is a must. But in regression problem, you are optional. You apply linear either you apply linear activation, or even if you don't apply, it is okay, because whatever number comes without transformation, you can show it in in a regression type of problem. But here you want all the values between 0 and 1. So sigmoid function transformation is applied. Now here when we do classification problem, at the time of compilation, you have to give this compilation. Loss function will be binary cross entropy. So now let us take it for granted. What is binary cross entropy? Take it for granted for this problem. When we'll discuss advanced topics, that time we'll discuss what is log loss, what is binary cross entropy, why we use it. And so right now you take it for granted that if it is a binary classification problem, then we use loss function as a binary cross entropy. Now my question to you, all of you, is, when we did linear regression, what loss function we used? Anybody? What loss function we used? Yesterday only we did. What loss function did we use for linear regression?
Sir, RMSE.
Yeah, RMSE we use, right? Root mean square value we use. So what is root mean square value? Very simple. Like y actual minus y predicted whole square. Y actual minus y predicted whole square taken for all the points. So sigma of that taken across all the points. That's what we took, right? So here the loss function is different, and I have promised you that when we'll discuss advanced topics in neural networks, that time we'll take this in detail, that what is log loss, what is binary cross entropy, when to use what. So all these things we'll discuss. So right now, take it for granted that for binary classification problem, always you will take binary cross entropy. Then optimizer is same, Adams, and this time we are giving matrix as accuracy. So matrix we are giving as accuracy. So I want to ask why we have given accuracy and not as precision recall. Why we are not given precision recall as matrix? Why we have given accuracy as matrix? Can anybody answer this question from our logistic regression discussion? Why we have used accuracy? Why we have not used precision, recall, or sensitivity? Tell me that. I want to know the reason of you using accuracy here. Anybody?
Sir, it is the ratio is 70 to 40.
Yeah, 60-40 ratio is there.
Yeah,
So
yeah,
classes are very balanced, right?
yeah.
Reasonably balanced. It is not 100% balanced, but reasonably balanced. So in that case, accuracy is a good measure to take. But if class imbalance were high, say 95-5, 10-5, 90-10, in that case, we can use some other measure. Okay, not accuracy. Accuracy is not a measure in that case. So then we use that. This is a different. This is a model. This is a simple function we have created to run to create the model. Now after that, it is the same thing. Then estimator is equal to Keras classifier. Yesterday we took Keras regressor. So this is the classification problem. We are taking Keras classifier. So same thing. Build function is equal to create baseline, which is this function, which we created just now. Epoch 100, base size 5, verbose 0. K fold also same thing. Stratified K fold and split equal to this time. Last time we took and split equal to 5. So this time and split we took 10. So shuffle is equal to 2. Shuffle means while creating the splits, shuffling like randomly records will be selected. So we want shuffling to be done. Okay. So now I want somebody to answer. I have taken epochs as 100 and split equal to 10. So totally how many models will be evaluated? Epochs as 100 and models as 10. So total how many will be evaluated models?
1,000.
Yeah, 1,000. Yesterday it was split equal to 5 and epoch 100, so 500. So today it will be 1,000 models, right? Then same cross validation score estimator, we have to take whatever we have created here, estimator, X trend, Y trend, and CV equal to K fold. It is standard code. All this standard code only which we used yesterday. All this standard code. and all this baseline we have taken, but this time we have taken scoring metrics as accuracy. So this time some I think default is accuracy. So this is what we are getting. Standard deviation we are getting as 9.2%. So same thing like this estimator object will not have your predict method. So we'll do like once more we are doing estimator.fit. Once more we have to do. And once we do this, once we do this, then we can use this analyze function in which we do predictions. So once we use analyze functions, so analyze function is plotting confusion matrix and precision recall curve. So I want to give you one homework today. You need to write down a small thing about what is the precision recall curve and what is its physical signification. How to interpret a precision recall curve. How to interpret a precision recall curve. It is not that easy. You have to do some web research. So I want you to do some web research and find out how to interpret a precision recall curve. That is one thing. Then another thing is that after below that, simply we have plotted one ROC AUC curve. Another question is how to interpret a ROC AUC curve, which is plotted here. Okay. So this is what this analyze function is doing what? Same function. So it is doing predictions, and based on prediction, then it is doing some confusion matrix. And once you have confusion matrix, you have you can calculate all these matrices because you have straightforward formulas to calculate all this. So that's what are being done in analyze function, which you can see later. So we have done ROC AUC, and so we have done this ROC AUC curve. And one more thing I want to tell you. Here, while giving first time when we said cross validation score, we did not use any scorer. It was a default scorer, whatever default scorer it used. Now next time we have evaluated this cross validation, same cross validation we have done. See the same code. Code is same. See till here the code is same. Code is same. See the code is same. Both our code are same. But this time only difference is that we have given scoring. So scoring as we have given ROC AUC. So we wanted to check how much based on ROC AUC, how much is the mean value which is coming. So mean value is coming as 0.84. So standard deviation is coming very less, 0.08, and mean value of ROC AUC is 0.84, which is good. So Malini Madam, please now note down two questions: how to draw and how to draw a precision recall curve. Number two, how to interpret a precision recall curve. Number three, how to plot a ROC AUC curve and how to interpret a ROC AUC curve. So these four questions means you have to go. We give code also. Huh? When I say how to plot a ROC AUC curve, you have to give the code also. Okay.
Yes.
So just note down these four questions. But I am not loading you too much today. So these two questions, if you do today, I think you are done. So I think then this train and test we have done analyze. Same thing has been done on test data. No, it is plotted. Same thing has been done on test data. Same analyze function we are using. Same estimator which we have fitted earlier. We are using on test data. Same things have been calculated. Precision recall curve, confusion matrix, and all these different model measurement parameter we have calculated, which are simply based on confusion matrix. And then same ROC AUC we have plotted, and we are getting this ROC AUC curve. Okay, so ROC AUC is coming as 0.96. 0.96 is coming up. ROC AUC here, and in train how much it is coming? In train also it is coming as 0.99. So 0.99 in a train and 0.96 in test. So it is within 5%. Train is 0.99 and test is little below 0.96. So within plus minus 5% it is lying. So that we can say that it is overfitting is not happening. So what is the condition for overfitting? Test score should not be outside plus minus 5% of train score. So suppose train score is 90, I can accept test score between 85 and 95. It should not go up beyond that. Okay, because sometimes we see that test accuracy by chance comes more than train accuracy. So we keep plus minus 5 of train score to see overfitting. So that is what we have seen here. Overfitting is not there because they are within 3%. So same thing they have plotted. Now we are doing another model which we did same thing, same model we are doing yesterday's model. Same standard scalar we are importing pipeline. Same pipeline code yesterday which what we did. Then same pipeline was the same thing we are doing, and same thing we are that pipeline code we are using it as estimator for that same estimator model. See, for estimator baseline, create baseline means create baseline means estimator create baseline. Here, see, here also Keras compiler we use create baseline only. Create baseline. So this same function as this create baseline, which we simple model we have created, and here what we have done to that simple model we have added a standard scalar, and the same thing estimator, same estimator we have appended a standard scalar, and to that we have appended a Keras classifier. So these two tasks we are doing simultaneously. So we have created a pipeline, same yesterday's code pipeline. We are using stratified k-fold, same thing, 10 split equal to 10. Now instead of estimator, we are using pipeline as the model. We are doing cross validation score, and then same code actually. Then cross validation score once we are doing with RUC IUC, and now here you see in the last time what we did. Last time we did this fit method on. Last time we did fit method on just a second. Estimated, yeah. See, last time you see this we did estimator fit method on estimator. But here since we have created a pipeline of two operations, scaling and model making. So that this time we are using pipeline as the model. So that same fit, same things are repeated. And then after that same things, then we have revised the model. So even smaller model is created. So this time what he has done, number of dimensions are 60 and neurons he has kept only 30. Some experimentation he is doing. So I will suggest you guys to read whatever Puraswani sir has shared yesterday. He shared some two good articles. So it gives a relationship between a number of input dimension and number of neurons, input neurons. So even if input dimensions are 60, he has put only 30 as the input neurons. So yesterday we saw it was more, right? Input dimension was X, and maybe the neurons he has kept was 1.5x, more neurons he kept. This time he has kept left. So you can keep both. The more also you can keep less also. Means it is not necessary always that if your number of input neurons should be equal to the number of input dimensions. If input dimension is 60, you can keep either 30 as input neurons in input layer, or you can keep even 90. You can keep both. We have seen that. So you have seen the effect. So when you go do at your home, just compare the accuracy of previous model to this model, and in same pipeline code, same thing repeated. Then next model, he has made one more model. Next model, he has added this model, same thing we see yesterday also. He has added one more hidden layer with 30 DS neuron. One more hidden layer is added, larger model. And in that hidden model, see, compilation and all is same. Loss is same, binary cross entropy, optimizer is Adam, same, everything is same. Only thing what he has done, he has put one hidden layer. Same, all code is repeated. Again, same things are plotted. So totally with 3 models you can compare with each other. Okay, so these 3 models you have created, and models are almost same as yesterday's model. Only point of difference is there, which I am explaining you. Instead of MSE as loss, we are creating binary cross entropy in classification. Optimizer is same. And matrix, there was R2, we are keeping here accuracy. And another difference is that last output layer activation function is sigmoid here. So in the regression problem, we said there is no optimization, there is no activation function required. Or if you want to put activation function, put it as linear activation function. So here we have to use sigmoid. Compulsorily in a binary classification problem, compulsorily you have to use sigmoid. And if it is a multi-class classification problem, more than 3 classes, 3 or more, then that time we use big brother of sigmoid, which is softmax. Softmax is nothing but a similar function, but more generalization of sigmoid. So, madam, actually, note down one function. One more question. What is sigmoid? What is the formula for sigmoid function and softmax functions? What is the formula for sigmoid functions and softmax functions? And what is the difference between them? So these are once more you need to put these 3 questions, you put 3-4 questions you put as a next week's exercise. So I think we are done with classification. So modeling is same, except that activation function in the output layer is different and loss function is different. Apart from that, all coding is same. So that's why I said it is a short class. And so I think we finish with this. Yeah, and one more important classification. One important difference is that for classification, all model evaluation parameters will be different because you have confusion matrix and hundreds of other sensitivity, specificity, precision, recall, ROC, AUC. Then you have PR AUC. Then you have F1 function. Then you have a lot of other functions are there, right? Accuracy is there. So all these things are, but you have to see this thing that this model evaluation parameter, model evaluation function, which I have highlighted here, they are same for any classification problem in machine learning or deep learning. So even for logistic regression, they are same. Even for random forest, they are same. Even for XGBoost, they are same. Even for decision tree, they are same. Even for ANN, they are same. Even for CNN, they are same. So for every classification problem under the sun, your model evaluation matrix remains the same. And for every regression problem under the sun, whatever model it is, you use R square and adjusted R square. So these 2 things are universal. For regression, you use R square and adjusted R square as model evaluation parameter for any model. And similarly, for any model classification problem, you have to make confusion matrix first. You have to plot precision recall curve. You have to plot ROC AUC curve, and you have to evaluate all these kind of parameters like PR AUC, ROC AUC, log loss, F1 score, sensitivity, specificity, precision, recall. So it's very simple. Once you understand once you understand fully one regression problem, once you understand fully one classification problem, irrespective of model, the model evaluation parameter remain the same. That is one good thing. So I think with this, whatever I wanted to cover in the class today is covered, and many of these things I think some of you might be still confused about what is the code, but there is no solution to it. I cannot beyond this I cannot explain you in the class. Now you have to go home. I share this code file with you, and you have to try yourself. Then only you will fully understand. You have to hand code this with your own hands. You have to code it. Then only you will fully understand. In class, I cannot explain you like a theory thing or like a English story or Hindi story. I cannot explain you fully in the class. So you have to code yourself. Once you do homework at coding, that time these things will be 100% clear to you. So homework and self-study is a must. You have to code with your hands. Then only you will get skills. In the class, it is a kind of introduction you can take. It was just to make a little bit familiar with the code. That's what I can do in the class, not more than that. To learn fully, you have to code yourself. So I think with this, I end my whatever I wanted to cover, I have covered, and I keep it open for the questions for a couple of minutes. And if no questions, then we can end the class. Anybody, any questions? Shrutika madam and many others, Shailesh Katre, Shrutika madam, many of you have to submit last week assignment you have not submitted.
Last week submitted.
You submitted, yeah, you submitted. Shrutika madam, you have to submit.
Yeah, sir, I have to submit.
Yeah. Madam, they don't do all these things because you will not learn otherwise.
Yeah.
So please submit it.
Mhm.
And Puraswani sir, you have to also submit the assignment last week's assignment.
Yes, sir.
So please submit it.
Yes, sir.
Otherwise, how you will learn? Yeah, I cannot cover everything in the class, no? So, and who has not submitted? Lakshmi Narayan Sahu has new, so I will not ask him to submit. So, Malini, Shrutika madam and Puraswani sir, I will explain that. I will expect that you submit in next 1 or 2 days, right? So, Malini madam will share today's homework with you. 4 or 5 questions, simple questions. That is to make familiar with. That is to make you familiar with regression model evaluation. That's why I have given that. And that is submit by next class, next Saturday. Okay. So, any questions here? Puraswani sir?
No, sir.
Shrutika madam, Malini madam, Shailesh Kadre, Lakshmi Narayan Sahu. I think you are not in the theory class, so you might have many questions, I think. So that is the challenge. Sahu, you are there? Okay. So I think if no questions, then we can end the class. I say exactly same coding, yeah, no difference. Only activation function for output layer is different, and log loss loss function is different. Only these two things are different. Rest 100% same coding. And once you do make the model and do the compilation and everything, then of course this model evaluation parameter will be different because this is a classification problem, and whatever we did yesterday was regression problem. So model evaluation parameters will be different. But if you use this study analyze function once at home, how it is written, analyze function. Once you study that, once for all, you can for your rest of your career you can use the same analyze function for any classification problem. You have to use the model. You have to use either xtrain or xtest you pass, and then you just give the title. Same model function you can use remaining of your career, data science career. Same thing for same analysis function we have for regression also. So you have beautiful code already available with you. You need not write it. Only thing which you have to write is this function, how to create a function, and then estimator and this. But once you learn this code, almost all kind of classification problem which you do with the help of ANN, a similar code will apply. That also is similar. That is also not going to change. So, Malini madam, you want to share how you increase the accuracy of your model?
Yes, sir, I can share.
Yeah, please share your screen and show everybody, madam. So, madam has created one model, and from yesterday, I think we were getting accuracy of 84% or something, and madam has improved the model and she has increased the accuracy to 88%.
Can all of you see?
Yeah, we can see, madam. We can see, yeah.
So I just, on similar lines, I created a function called wider model extra layer. So here, same sequential, and then into the dense function, I added one more layer. If you can see this here.
Yeah.
I just added another layer with 10 neurons.
Neurons, yeah.
And the previous one's output was 20 neurons. So the input dimension would be 20. The kernel initializer, the weights are just the same. Activation function also.
Madam, please double check.
Yeah.
I think in the second dense layer, you need not give input dimensions again. Just double check it, madam.
I'll check it, sir.
You check it.
I just
Soman, you remember whether in second layer where you have to give input dimensions or not?
No, sir. Actually, it is not required.
Yeah, it is not required. Yeah, that's what I remember. Only
but-
first layer you have to give input dimensions.
okay, I'll check it.
Ma'am,
sir.
but whether you put it or not, it doesn't matter because obviously that layer is connected to the previous layer, it will automatically
Automatically
calculate
take,
if
because
it is
first
receiving.
your first layer, which is input layer, is anyway having 20 outputs, right? 20 H values.
Yes.
So that 28 values, H values will automatically go to the next layer.
next
It is
layer.
all flows like a river. Okay, so you need not give an input, second time input.
Okay, sir. I'll
No problem though, ma'am, it is no problem though. The code is correct. It is not interfering with your score in any manner. It is correct code.
So,
Okay.
madam, you have done one nice NN you have made actually, and I want everybody to practice like this and create. I want you add 2 more layers, no? Why you want to put only 1 layer? Put 2 more layers and see how much time it takes to execute.
Yeah, actually it took, cell by cell I executed. This one probably
Yeah,
roughly about 1 minute 45 seconds.
good, madam. It is a very small model, so it is taking less time. But if you add 2 more models and see now how execution time probably will increase by exponentially, it will increase. What I suggest, you add 2 similar layers, same thing you copy.
Okay.
Model dot 8, dense 10, same thing you copy with 10 neurons, 2 more layers.
2 more layers. Okay.
And try to run, see how the execution time and accuracy and all varies.
Yes, sir.
So you have to gain some experience with it, na?
Yeah.
So same to you, Shrutika madam, you also, Shailesh Kadre, same thing. Understood, na?
Okay.
So you
Yes,
add, do experimentation like this, yeah. Good, yeah, madam, good, nice, appreciate. Thank you so much. So if anybody has any question, then we can end today, right? I think it is already 1 hour over.